The Smart Landing Pad is a vision-based system meant to assist drone pilots in landing drones where precision is required, such as landing into a dock or mount. A camera is integrated into the center of the landing pad, allowing it to acquire a visual lock on the drone, relaying information back to the drone pilot, ensuring a safe touchdown. Due to the camera's integration into the landing pad, a direct line of sight to the drone is not required, making it especially useful in situations where vision is limited. A light is mounted around the camera which shines onto the drone. Due to the retroreflective tape, the reflection is very visible, allowing for the drone to be accurately located. Firstly, a drone preparing to land hovers near the landing pad. At this stage, GPS precision is enough. Secondly, once the system locks onto the drone, it displays all flight data onto the heads-up display. This includes altitude, heading, and position of the drone. Lastly, seeing the data displayed through a pair of virtual reality goggles, the pilot can accurately guide the drone onto the landing pad with more precision than would otherwise be possible. Example uses of the system include landing parasitic drones onto a search and rescue vehicle where the drone itself is not directly visible, nighttime operations where there's not enough light to fly the drone by sight, and remote operations where the pilot is far away from the drone and cannot see it with other means. Because the system is ground-based, drones that fly in dangerous situations become more expendable as there is less equipment on board to lose in the event of a crash. The code of the system can be separated into 4 main categories: data input via the camera, image filtering to determine the drone location, real-time calculations to determine the flight data of the drone, and data output, overlaying the flight data on top of the image for an easy-to-read, intuitive user interface. The program first takes a snapshot from the camera. It then analyzes each individual pixel of the image, looking for specific colors. This is called an HSV, or Hue Saturation Value Mask. The hue defines what color it is, in this case green. The saturation defines how intense the color is, whether it's an intense green or a washed out grayish green. Lastly, there's the value that determines whether the color is bright or dark. Specific pixels that fall into a certain range of all of these values are made white. The remaining pixels are made black. This is what the image looks like at this step. The filtering isn't perfect and lots of noise can get through to the background and have the same colors as what the drone should look like. To filter out all the noise, all groups of white pixels are mapped into blobs. Only specific blobs are considered. For example, a blob's width must be around equal to its length, it must be of a certain size, etc. Once all these blobs are highlighted, the program must look at comparisons between blobs, as a drone would be 2 blobs. In any given pair, one must be around twice as big as the other, and the distance between them must be less than the diameter of the bigger blob. After filtering this way, the program is able to make out the location of the drone on the screen. To calculate flight data, it looks at the properties of the blobs. Firstly, the program draws a line from the bigger blob to the smaller blob. This line represents the heading. It then looks at the size of the blobs. Secondly, using trigonometry, it is able to determine the height of the drone. Finally, by calculating the center point of the blob and comparing it against the center of the screen, it figures out the amount that the drone must move laterally. And finally, to make all of this data usable by a pilot, it displays the camera image with all flight data laid over top. One specific area of the code that I'm proud of is the error vector calculations, or the offset in relation to the drone itself. Just getting the x and y values of the drone on screen is not enough. If the drone is facing to the left, for example, being under the center of the screen would mean that the drone actually has to move to the right. To solve this issue, trigonometry and linear equations were used. The program first determines the slope of a line in the direction of the heading. This line represents the direction of the drone's front-back vector. The line must pass through the drone itself. A perpendicular line is then drawn, representing the direction of the drone's sideways vector. This line passes through the center of the image. A new point is calculated where these lines intersect. The distance from this new point to the drone is the pitch error magnitude, and the distance from this new point to the screen center is the roll error magnitude. One particular challenge was getting the program to run smoothly. At first, it was plagued with latency. It would jitter and make the output screen not as useful. To combat this, I first tried to downsize the image, as this would mean less calculations. This proved useful, but accuracy would be lost when flying high above the camera and it wouldn't always be able to lock on. I then tried to switch between a high-resolution mode when the drone is far away and a low-resolution mode when the drone is close, but this switching also induced too much lag. In the end, I made the program only process the flight data every 5 frames, as data being shown faster wouldn't be of much use to a pilot anyways. This means that although the data is updated less frequently, the image is smooth, allowing for a better user experience. So there you have it, the smart landing pad. In the future, I hope to automate the entire process, allowing for a drone to take off, fly on its own using GPS guidance, which I've done in the past, and then come back and land onto the same spot with the help of this system. Currently, it is a pilot assistance system, but a helpful one nonetheless with a variety of applications.